Hello, and welcome to this video on types of bonds in resistance welding in the resistance welding playlist. To begin with, let me start by sharing the screen so you can follow along with the PowerPoint as we go. My name is Girish Kelkar, and I am a welding consultant operating as WJM Technologies. Additional information about my consulting business is on the web at welding-consultant.com. There are three types of bonds which can be made, which can be considered metallurgical connections, and that includes solder or braze joint. I have lumped solder and braze together because they are similar in the sense that in both instances we are adding another alloy which melts, whereas the parent metals don't melt. Solder alloys are those that melt below 450 degrees centigrade, and braze alloys are those which melt above 450 degrees centigrade. For most applications for soldering using resistance welding equipment, the solder alloy is either pure tin or a tin-based alloy. The other joint of interest is a solid-state bond. This is a type of bond where the metals which are being welded don't actually melt. They become soft, they are pushed together, but they do not melt. The third type of bond is a fusion weld, where the metals melt and mix and solidify to form a bond. Let's look at examples of all three. The first one is a solder joint. This is an example of an electrical wire welded to a copper trace on a circuit board. When I mentioned the word welded, in the sense that we are using resistance welding equipment, even though the bond itself is a solder bond. So this bond was made by placing one of the electrodes on the top of the wire here, one of the electrodes below the copper trace, and when current was passed through that stack, the tin plating layer, which was on the copper trace, melted, and due to wetting action and capillary actions, the solder plating actually engulfed the wire and trapped it, forming a good solder connection. A similar application is for resistance brazing. Here I'm showing you a schematic on the left where two components, they're made of copper and they have a silver plating on top and they have to be joined together. We have two electrodes, they're both tungsten electrodes, and they are pressing the two parts together, and there is a braze foil in between as shown over here. During the brazing process, as current passes through these electrodes, tremendous amount of heat is generated to the point where the braze alloy melts and flows into these channels provided on one of the components. There are some locations where you can actually still see the silver plating, which is the original plating on the two components. In other locations, you no longer see the silver plating because that silver plating has dissolved into the braze alloy, which happens to be a silver copper braze alloy. The third example is a solid state bond. A solid state bond is a bond formed directly between parent metals. During the welding process, the heat generated is enough just to soften the parts and not enough to melt. So you bring it up to 70–80% of the melting point, and the welding force, which is provided by the resistance welding equipment, pushes the parts together and literally forges them to form a bond. During the welding process, as the parts become soft, there is some amount of deformation of the parent metals, and that deformation leads to break in the oxide layers. The heat also burns away any contaminants that might be present at the weld interface. With the breakage of the oxide films and burning of the contaminants, fresh metal from both sides is exposed to each other, and these atoms come in contact and they're forged together. And as the current is reduced and cut down to zero, the bond cools and forms a strong connection. Keep in mind that solid-state bonds are most common in small-scale resistance welding. So if you're doing small-scale resistance welding, which I have elaborated in an earlier video in resistance welding, such for applications such as medical devices, sensors, electrical connections, solar cells, and so on, you are quite often either welding dissimilar materials or welding very conductive alloys such as copper, silver, gold, and so on. Either case, it's a benefit to make a solid state bond instead of trying to form a fusion weld. Here's an example of a cross section of a solid state bond between two pieces of steel. And we can see that we can clearly see the interface between the two parts. We do not see a fusion nugget that would be typical of a fusion bond. We do see a slight change in color of the two components and indicating there is a heat affected zone on one side and there is some amount of heat affected zone on the other side as well. So this is a classic solid state bond where you don't see any fusion, but you do see some amount of heat affected zone on either side. Here are some examples of conventional fusion welding, where the picture on the left shows a cross-wire weld. Cross-wire weld is a weld which made between two wires which are at perpendicular to each other. And you can see that the welding heat has produced some amount of fusion. And we can see that the fused material is getting squeezed out from between the wires. The other typical type of weld in fusion welding is when you're welding two sheets together. When you put those sheets together and have two electrodes, one on the top, one on the bottom, and send energy through, we can create a fusion nugget. A fusion nugget is a volume of metal which had fused during the welding process. So this volume over here was at some point in liquid state during the welding operation. As you cut down the energy to zero, the fusion nugget solidifies, and that can be seen as a separate entity in the cross section. You notice that the fusion nugget has not grown all the way to the edge. So when you look at these welds from the outside, you sometimes only see a faint indication that there is a weld on the inside. The nugget formation can be a little bit of a risk if you're welding dissimilar materials, and mixing of those dissimilar materials could form either a brittle zone or an intermetallic. Either way, the weld nugget becomes quite brittle, and when you test it, it can lead to failure at a much lower strength than you had anticipated. So fusion nugget, while good in some applications, may not necessarily work in all. Here's a good example of that, whether we want to go with solid state or fusion. On the left, I'm showing you a cross-section of a component where a MP35N strip is welded to a stainless steel body. And we can see a clear line along the interface. There was a small bump or a projection on the MP35N, which has since collapsed, but we can still distinctly see the line at the interface, indicating that it is a solid state bond. While this weld was strong, we attempted to increase the strength by putting more energy into the weld, and we did find that at higher energy levels, we actually created a fusion nugget. So there was actually fusion between the two components. However, we did find that the weld with higher energy was actually weaker in strength compared to the weld which was considered a solid state bond. And that is likely due to the fact that when you mix dissimilar materials in a fusion zone, you are likely to form a lot of intermetallics which tend to be brittle and result in a much lower strength for the weld. In summary, resistance welding is the only process which can make all three types of bonds. Resistance welding can make solder or braze joints, solid state bonds, or fusion bonds. So this is very, very unique to resistance welding. There are other processes which can make one or two of those. For example, you can use laser welding to create fusion welds as well as braze joints, but you cannot make solid state bonds with laser welding. The type of bond cannot be evaluated by mechanical strength alone. It does require weld section analysis. This is a very important point. It is a conventional wisdom that If the weld is strong, it must be a fusion weld, but that is not true. In fact, in majority of the small scale resistance welding applications where we are welding dissimilar materials or conductive alloys, we typically prefer to make a solid state bond. And that helps in many ways, especially for dissimilar metal welding, and also helps to reduce the residual stress because we are not going to a very high temperature. So we are now cooling from a slightly lower temperature, and that reduces the residual stresses in the weld. So this is something to keep in mind, that resistance welding can make all three types of bonds. However, in small scale welding, where you're welding small parts, typically, which you hold in your hand, and sometimes you even have to sit in front of a microscope to make these welds, those welds often tend to be solid state bonds. And again, the only way to find out what kind of bond you're forming is by making good cross sections and reviewing the details in there. Thank you. If you're interested in learning more about welding and joining, please subscribe to this YouTube channel by clicking on the subscribe button below. Videos on specific topics are in the playlist on this channel, so you can review those videos and see if you find something interesting, and wishing you the very best. Thank you.